Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 9, Atomic Structure and Periodicity, Part 2. In this video, we're primarily going to be talking about quantization and how that applies to hydrogen line spectrum. Pause here. So we talked about the dual nature of light in the last video. This is really just the continuation of that, which is wave-particle duality. Everything that is a particle can also be described as a wave, and everything that is a wave can also be described as a particle. What makes something wave-like versus particle-like is really its behavior. So something is behaving in a wave-like behavior, or wave-like manner rather, if it has indefinite location, whereas something that is more of like a particle, let's say like a baseball, has a definite location. If a baseball hits your hand, it is definitely in your hand. If you have your hand out and you happen to see light upon it, yes, that light is on your hand, but it's also a lot of other places too. And then how wave-like something is depends on its mass and its velocity. In general, things with very low mass lead to more wave-like properties. I'll elaborate a little bit more on this in class. There is actually a mathematical relationship for how wave-like something is, but it's just not that important enough for me to include it in the video. Pause here. So certain quantities, such as energy, which is going to be our most important one, can only occur at discrete value. What they mean by a discrete value is that the energy could say be 100 joules or it could be 200 joules, but it can't be in between the two. And this has to do with the fact that electrons are really wave-like, or I'm going to start referring to them as being something that is quantum. Notice that the word quantum and quantization have that same root there, quant. And then if something is not quantized, then the values are said to be continuous. But we're going to focus on quantized values in this video. Pause here. Okay. So when a light hits a material, the material is able to emit electrons that have the same amount of energy that it is hit with, but it's not continuous. So what ends up happening is that if you bombard a sample with energy, the electrons will pretty much fly off at these discrete values. And we can actually measure these discrete values by measuring the wavelength of light that is emitted. So an atomic line spectrum, that is actually measuring the wavelengths or the frequencies of light that is emitted when a sample is bombarded with energy. We can actually calculate this only for hydrogen. The math becomes way, way, way more complex for other sorts of elements. And really, it's not something we're going to need to get into in this class. But we're going to use this equation here to calculate the energy of a photon that is going to take an electron from one energy level to another energy level. If you don't already know what the energy levels are, we'll talk more about them this chapter, but think of them as just which ring the electron is in. We'll get into that in much more detail a little bit later on. Let's do some calculations for now. Pause here. Okay, so let's work through that. I've just got the same equation that I had before. So I'm going from n is equal to 1 to n is equal to 2. By the way, if you didn't already know what that triangle means, that is uppercase delta in Greek. That means change. Anytime you see the symbol delta, it just means change, or another way you can think of it is final minus initial. Hence why you've got the final and initial here. All right, so let's get back to that. So we are going from n is equal to 1 to n is equal to 2. So my final one, my NF is 2, my Ni is 1. So then all I have to do is put this in my calculator. And I got 1 point. These are not going to be sig fig questions, by the way. These are pretty much all constants. But just to keep it in the spirit of what we've done in class, I'll do 4 sig figs just because that's what is in the question, but this would not be a sig fig question on a test. So I got 1.634 times 10 to the negative 18th power. I got a positive. You don't have to include the positive, but if it's negative, you do have to include it. It would be a good habit to include it, though. So notice I did include the positive. That means that energy had to be absorbed in order for this energy change to happen, which makes sense because you're going from a lower energy level to a higher energy level. pause here. All right, we'll work through this one as well. All right, so for the first one, we need the same equation we used last time, E is equal to HV. And then I'm looking for frequency here. And then I just plug right in. So I get 2.465 times 10 to the 15th hertz. And now I'm looking for wavelength. And I got 1.217 times 10 to the negative 7th meters. Thank you so much for watching and have a great night.